Hello everyone, welcome on this e-learning platform of Apex Institute of Physics. In this video we will talk about electric flux. This electric flux is represented by letter phi. So phi is used for representing it. And how it is defined, so let's discuss about it. It's defined as the measure of, this is measure of electric field lines, electric field lines passing through a given area, passing through a given area. So if area is known or a surface is known, then from that surface how many field lines are passing through, the measure of those field lines is known as electric flux. Mathematically we write this flux as definition goes d phi. If we write it as a d phi, which is a flux through a differential area, this is defined as E, that means electric field, dot ds, where ds is representing area vector. So this is flux passing through a small area ds vector. Now here we know this E is representing electric field, so that electric field is a vector quantity. And whenever we talk about area is generally considered as a scalar quantity. Here we are considering the area as a vector quantity. So we are performing a dot product between two vectors, and there are rules for dot product, you know, and as per the rule this is going to be E ds cos theta. Before we go further, we need to understand how we are considering this ds as area vector. S is representing area and ds is representing differential area, and arrow is indicating a vector. Now differential area vector ds will have its magnitude and a direction. As far as the magnitude is concerned, magnitude is ds itself, and its direction is ds cap, or which we can call it as a n cap. Now ds is going to be the magnitude of that area. Depending upon the element, we will consider that area element. And the direction is important here. We give the direction to that area to make this area as a vector, and the direction that we give that area is perpendicular to that area. Now to understand this direction, there is a figure 1 and figure 2. Let's talk about the figure 1. Figure 1 says this is a circular area. So if we talk about the area, that's going to be pi r square. If we talk about area vector, then there has to be direction which is perpendicular to this circular area. So that's perpendicular direction is n cap. So n cap is a perpendicular direction to that area, and it is in the outward direction. Figure number 2 will illustrate it further. Let's say this is a curved area. In that curved area we have taken this small element which is called ds, and its direction which is perpendicular, this perpendicular direction which is perpendicular as well as outward direction, this direction is n cap. Now this area will have a two direction, one inwards, another is outwards. So we always consider the one which is outwards. So to remember the differential area vector's direction, it is perpendicular to the differential area surface, and it is in the outward direction. This is how this area vector we consider. Electric field is a vector quantity. We have already talked about it, and we know, if we know the direction of these two vectors, then we can perform the dot product. So to take it further, we will say this d phi will be equal to E ds cos theta. Here cos theta is using angle theta, which is between vector E and vector ds. Now that means where we are calculating this flux, we must know the field direction at that location and area vector's direction. If we know these two directions, we can find theta. If we can find theta, we can go for this dot product. Now, in order to find out the total flux, so total flux is going to be equal to integration d phi, which will lead to flux is equal to integration E ds cos theta. So that is the formula for flux. Using this, we can find out the flux passing through any surface. Here we have understood E is has to be kept as a magnitude, ds has to be kept as a magnitude, cos theta has to be decided based on the theta. Now theta is the angle between E and ds. So these 3 and 4 picture will illustrate how we will measure the theta. Let's come to the picture number 3. 3 says E is pointing in the x direction, and this is a plane surface. This plane surface is inclined by theta degree from the vertical. So since it is inclined theta degree from the vertical, so the perpendicular of this is going to be s direction, which is going to be this one. So that is ds direction, or surface area direction. This is the direction of E. The angle between them is theta. So here we will be considering E ds theta, or if E is uniform, ds is uniform, so this integration can be simplified, right? So this is how we will measure the theta between E and S. In case of non-uniform cases, which is this, we need to perform this integration. So for instance, let's say this shaded portion is a surface from which we are interested in finding the flux, and these are the field lines that has been shown there. So field lines are going to intersect and passing throughout it, right? So what we need to do, we need to consider a small element on that surface. This white color element is a small element. Of this element, the perpendicular direction will be indicating ds direction. So here ds direction has been illustrated by perpendicular direction. Now this is the direction of E at that location. So by tangent we are getting the E at that location. The angle between them is a theta, so that becomes theta. So the flux through this surface is going to be integration E ds cos theta. Mind it, in the figure 4, when the element changes, theta changes. Theta changes, that means cos theta is a variable. Depending upon the field, E may be constant or variables, and the ds is a surface area element that requires twice integration. That means this integration in itself is a complex. Now this will be easier if either E or theta or a combination of these things becomes uniform over the surface, right? Now moreover, depending upon theta, this phi can be positive, can be negative, right? Or it can be zero as well. Now phi definitely is going to be a scalar quantity that is obvious from this dot product, because we know the dot product of two vectors always yields a scalar quantity. So it's a scalar quantity. Now flux can be positive, flux can be negative. Now when the flux is positive, that means we say field lines are coming outwards from that surface. So field lines are coming outwards, or flux is coming out. Now if flux comes out to be negative, that means we say flux is going in. So whether the flux is going in or coming out, it decided by the sign. So positive flux is flux outgoing, negative flux is ingoing flux. So this is the basic definition of the flux and its mathematical representation, and the definitions of quantities involved.